So let's do a deeper dive into K and P.
Right, exactly. So when we're talking about K and P, K of course is data, P is parity. P is going to be equivalent to the number of simultaneous volume losses that you can have without data loss, and it must be greater than 1. Now, if you're using subclusters, you may decide that or in larger clusters, when you approach very large scale, you may decide to split things up. So that's the number of simultaneous nodes you can tolerate to fail, or the number of simultaneous subclusters you can afford to have down. But ultimately, that's what we're referencing here: the number of items in the cluster, the divisions in the cluster you can have unavailable and still access your data. What K gives you control over is the space distribution. And ultimately, your efficiency is defined by the equation that we show you there, which is K plus P divided by K. That is your data footprint for the erasure coding scheme that you have chosen. It is worth noting that larger K and P numbers are going to require more resources in the form of CPU memory, and ultimately, like we just said, that the number of nodes that are needed to make sure that you can have that data available when requests come in to read it. And we have a simple table over here to the right, AJ, where we walk through the comparisons between typical protection schemes that are encountered in the field. You have your usual reps equals 2, reps equals 3, and then typically what people use for erasure coding is something along the lines of the ones we see the most, AJ, are EC52 or EC63, and the comparisons there. For the footprint multiplier, as we said previously, overhead for reps equals 2 is 100%. Overhead for reps equals 3 is 200%. The amount of storage that's needed, the raw storage that's needed to store a terabyte of data becomes 2 terabytes for reps equals 2, 3 terabytes for reps equals 3, et cetera. And then, of course, in the last column, we have the simultaneous volume loss tolerance for those protection schemes. But as you dive down into erasure coding, you see the magic start to occur. So let's talk about EC52 because that's a very common one. We talk about that all the time. And as we go into this scenario, you get your 40% overhead and so on. And let's talk about what happens when these fail. So in our example here, we have an EC52 scenario. You have 3 chassis or servers. Each of them have 3 volumes, and the encoding scheme used for data is 5.2, 5 data, 2 parity. This creates 7 segments total that are evenly distributed across the cluster as best as possible. In this case, best as possible is 2 segments on one, 2 segments on the other, and 3 on the remainder. And then there are 2 parity segments, and what that means is you can tolerate the loss of 2 of those segments in order to still read the data in the system. So in this case, you can lose any 2 volumes, or you can lose an entire chassis. You can lose chassis 1 or 2, but you can't lose chassis 3 because again, it has 3 as part of the remainder for the distribution. And the other key takeaway here is that if one of these chassis will fail, recovery will fail because there are not enough remaining resources in the cluster to reinstantiate the segments that are needed to true everything up for the objects that have been written in that fashion.